So welcome back. I guess this is the beginning of the 10th lecture in this series. So in the last 2 days, we've been talking a lot about individual molecules, individual reactions, and how you compute the parameters, the thermochemistry parameters and the rate parameters. And I'm sure that I didn't tell you enough that you would feel like you have the expertise to go ahead and calculate these yourselves. Some of you I know are taking Dr. Klippenstein's class. That will tell you more about it, but I guess even that might not be enough. Probably you really have to actually try to do some of these calculations yourself to really dig into it and learn it. I'll probably come back tomorrow and talk a little bit more about some of the issues just to keep in mind when you're doing those calculations. But I thought for now I'm going to skip ahead and talk about how do we combine all of these parameters that we have about individual reactions into an overall model. And there's quite a lot of intellectual challenge there as well. I have to apologize. When I was making the slides up for this presentation, I was running late, and I just cut and pasted 2 slide decks together, one after the other. But they had repetitive material and were not in the most coherent pattern. So I've rearranged things to try to make it more pedagogical. So you'll see that today. So I'm going to talk about the problem of mechanism construction for the first 2 lectures this morning. And then Professor Tianfeng Liu from the University of Connecticut is going to come and give the last lecture about mechanism reduction. So very often what we have is that we have to construct a model for our system. But then after we construct it, we discover it's so big that we can't solve it in the reacting flow simulation that we want to solve it in. And so then we're forced to reduce it. At every stage, there's multiple opportunities to make errors. If you get any of the parameter values wrong, you'll have an error. And you will have some of them wrong. So that's one type of error. If you forget to include some important species or important reaction in your mechanism, that'll be another kind of error. And then when you find you can't solve the mechanism, then you have to reduce it. There's a lot of potential, if you reduce it incorrectly, to get additional errors. And so a key thing to keep in mind in this whole process of trying to build models for anything, and in particular for this kind of chemistry models, is keeping control of your errors, identifying where the errors are, trying to quantify what they are, trying to keep the errors small for the observables that you care about. And that's like the background philosophy of this whole work, is trying to make sure that we have good numbers where we need good numbers, and we're neglecting things that we're allowed to neglect, and we're trying to make the model to be as a good approximate model to the physical reality. Again, this is much easier for me to say in 2 minutes up here than it is to actually do it in practice. Tomorrow, I'll continue on the combustion chemistry regimes, and in particular, I want to talk about 2 regimes. One is spontaneous ignition or compression ignition, and the other one is soot formation, because these are 2 of the most important regimes. Probably also talk some about NOx formation as well. All right, so here's the plan for the day. So the key thing is we're trying to make accurate gas kinetic models. And I would say that in the context of this whole talk, my presumption is you don't have enough data. You don't have nearly enough experimental data to determine your parameters. So you're going to get a lot of your parameters from a priori calculations, or maybe from estimates, and not without being able to refine them based on experiments. You're not going to have enough experiments. And so really you're trying to work on predictive models, things you could make a model and make a prediction even if you didn't have any experiments. And this is maybe a big philosophical change. So some of you in your life, probably you've measured some data and you fitted the parameters in some model to match your data, and you felt like that was what modeling is about. It's like, and I would call those models postdictive models. It's like you have a model that says what your experiment is after you've done the experiment. You already know the answer, and you're trying to adjust the parameters in your model to be conform to your experiment. And this view is different. Is if you have a model that has too many parameters, you're never going to be able to determine all the parameters experimentally. So right from the beginning, it's not about fitting. It's about do I know how to predict the numbers correctly? And in the context of predictive modeling, your view is you make a prediction, and the experiment tests the prediction. It doesn't train the model. It tests the prediction, and then it's like a validation. If you agree, you don't say the model's proven to be correct because the model has too many parameters. You can't prove it's correct with your limited number of experiments. But you can at least prove that it's not inconsistent with this one experimental data that you have. And then I'm trying to focus on systematic construction of reaction mechanisms. So historically, most reaction mechanisms are written down by people, and they wrote down the reactions that they think are important. And some people are more systematic than others. And in general, humans are not systematic. Most humans have a lot of trouble being systematic. And so if you look at even the most careful person, the most systematic person you know, if you look at the kinetic model they wrote, if you look at it really carefully, you usually can find some reaction they forgot, some mistake they made, and something. It's just the way humans are. We are not consistent. So here we're going to try to be systematic, first to lay out how you would be systematic if you're trying to do it as a human, and then say, well, humans are not systematic anyway, so let's make a computer do it. And a lot of the slides I'm going to show here I previously showed at a talk at the Gas Kinetics conference last year. All right, so our long-term project of the chemical kinetics community in general, and including the combustion chemistry community, is trying to make this gas kinetics into a quantitative predictive science. So historically, it was not. Historically, kinetics was primarily an experimental science. You measured a rate coefficient by doing a pseudo first-order experiment like I described, or doing some product studies. And you basically tried to find the simplest model that was consistent with your data. And you didn't worry about the fact that that model might not be faithful to everything that's actually happening in your mixture, because that wasn't the view. The view was, I have some experiments. I want to replicate the experiments. I might want to tweak the conditions a little bit around this measurement. And I want a model that's really for interpolation. And I don't need to understand everything. I really only care about the major species I measure. All this minor intermediates, who cares? So that was the historical prevailing view for a very long time. And Benson in the 70s started to point out that, A, it's hard to do enough experiments to get all these parameters. And a lot of times we can't get them. And B, we actually know a lot about the real molecules and the real intermediates, so why shouldn't we use that knowledge? And so he started to try to change the view. But at that time, people couldn't do quantum chemistry. They hadn't invented the density functionals that were any good. Computers weren't any good. And so he worked at a lot of empirical ways to kind of estimate things. But then it was a challenging thing because he's like trying to say, well, I should predict things. But then he says, well, actually, all the parameters I'm going to predict, I'm going to actually infer from some other experiments. So it was like a really mixed up kind of thing. If you read his textbook, it's kind of confusing because of that mixed philosophy. Here, now, you guys are lucky. We have good computers. People have worked out all the theoretical equations. And you can actually calculate stuff. And it's not really that challenging to do it. And so you can really take the a priori view, that we're actually solving the real fundamental equations and getting the real answers. So instead of doing the experiment first and then building the model, instead we're going to make the predictions first and then do the experiments to try to falsify the predictions. And that will be ways to find errors in the way we're making predictions. And if you could actually make predictions that were really good, this is really helpful because then you could do design. So you could design your combustor based on the chemistry model. If you believed it, if you believed the model was good enough, then you could design it to have the lowest possible emissions or whatever your target was. And also, already, these models are used for public policy decision making. So most of the regulations and laws and treaties about atmospheric pollution are all based on atmospheric chemistry models. And people treat them as models as true, and they use those to actually define what the regulations are going to be. And so that's a very important case because you really can't afford to do experiments on the atmosphere because you're not going to say, well, let's pollute it this way and see if it turns out good or bad, right? Next week we'll try to pollute it a different way and try it that way. We'll compare which one's better. Right? It's not practical. You have to switch to the predictive view. But in almost any problem, if you can switch to the predictive view, it's a lot better. So I mean, people, they design race cars and bridges and stuff on the computer now. You don't actually try. Well, we'll build 3 different bridges across the Hudson to see which one's strongest, or that's not the way you do it, right? You do it in the computer. And so we'd like to do the same thing with chemical systems. And the key then is to have accuracy, because if you're going to make your designs and you're going to rely on the computer to make the designs, they better be right. So like if somebody designs a bridge and they use the wrong Young's modulus for steel, then there could be a lot of bad results, right? So you have to have, the parameters have to be right within some error bars. The structure, your equations have to be right. And so then you're really worrying about the correctness of the computer model. It gets to be very crucial if you're actually going to rely on it to make designs. And in the chemical industry and in combustion, if you make bad designs, you have potential for really catastrophic failures. So, I mean, similar to a bridge falling collapse, you can also have, a chemical reactor explode. You can have a rocket ship explode. You can have an scramjet engine flame out, and the poor pilots, plummeting to Earth. I mean, you get a lot of bad things can happen. So you really want to make sure you know what's going on. All right. And it's also great for improvements, too. I mean, you can do interpolative improvements based on empirical models. But if you have a better model, it has better extrapolative power. You can take sort of bigger steps, not be so incremental in your improvements. All right. However, predictions are really hard. And as far as I know, the first guy who realized that you could use the fundamental equations and predict chemistry was a guy named Dirac. He was a really smart guy. And he published in the Proceedings of the Royal Society in 1929. He said, now we have the underlying physical laws necessary for the theory of a large part of physics and all of chemistry are completely known. We know everything, all the equations for chemistry. He suddenly realized this, 1929. He published this to the Royal Society. He says, I've got it. I have all the equations for chemistry. Here's the fundamental equations. Just go ahead and use them. But then he says, there's a difficulty is that the exact application of these laws leads to equations that are much too complicated to be soluble. So basically he says, we have an existence proof. We have the equations. Sorry, you can't solve them. Too bad. So that was Dirac's opinion in 1929. However, the chemists didn't read the Royal Society journal, and they didn't know that he told them it was impossible. So they just kept on trying to solve it anyway. And so in 1935, the transition state theory was formulated, and the first basis set methods that were pretty good for solving the Schrodinger equation were invented, called Hartree-Fock theory. So that's just 6 years later. And people kept on working on this, plugging away. And so by the 1960s, the coupled cluster method, which is a really good high accuracy method for solving the Schrodinger equation, was developed. And the density functional theory equations were formulated too, the Kohn-Sham method. And also, the transition state theory got really better understood, and a version of it called RKM theory was written down by a guy named Rudy Marcus, who happened to be the thesis advisor of Dr. Klippenstein. And so by the 1960s, we had the equations, and the ideas of the algorithms were formulated. But in the 1960s, a computer that's like as strong as your pocket calculator would fill this whole room, and require a staff of 20 people to take care of it, and had a memory, about as much as you could write down in a notebook. And so you really were very limited in what you could do. And so they really couldn't, they had the equations, but they couldn't do much. But then in the 1980s, they invented supercomputers. They also made a very crucial advance. Most of the chemical kinetic equations turn out to be stiff ordinary differential equations because there's a large separation in time scales between the very reactive intermediates, things like H atoms and OH, and the very stable molecules like alkanes. And because of that mismatch of time scales, it turns out that ordinary differential equations solution methods don't work. And if you just try to run it with like Runge-Kutta or something, you'll get the wrong answer. It won't actually be able to integrate it. Or if the code's good, it'll tell you I can't integrate this. The time step will keep dropping. At some point, it'll say, sorry, hitting the numerical round-off error in the calculations. Too bad. But a guy named William Geer, who actually I think was working right down the road from here in Princeton, he figured out the first algorithm that could solve the stiff ordinary differential equations. So therefore, if you could write down the chemical kinetic equations, at least for a homogeneous batch reactor, you could solve them. So that was a big advance. And immediately following after that, the chemist immediately recognized this is super important. And a group at Livermore developed the Chemkin software, and they had at least one student of Gears was there. So he knew all about how to solve the stiff ODEs, and there were a bunch of people there who knew about other methods for solving reacting flows and knew all about the chemistry, and they all worked together and they wrote the Chemkin software. And the Chemkin software later was licensed to a company called Reaction Design, and then they got bought by ANSYS, so nowadays you buy it from ANSYS, but originally it was from the National Labs. And done as a skunk works. There was like no permission by the management of the National Labs to make it. And they had a lot of trouble, political trouble, because they spent their time on the software. They were supposed to be working on something else. But they thought it was really important, and they did it, and it was really important. And eventually, the labs trumpeted about their great success in making this great software, and the managers acted like, oh yeah, of course, I always wanted this all the time. So that was the 1980s. In 1988, the first good first good DFT functionals were formulated, and by the early 1990s, they had been incorporated into good computer software. So then, by early 1990s, you could actually run a good, calculated good VFR to get geometries, get vibrational frequencies, pretty good at that time. By the late 1990s, the B3 lit method functional had become available, and some other good functionals, and the software had gotten better. So by late 1990s, it was like not hard at all to do good calculations of vibrational frequencies and geometries of molecules and define transition states. And so people then realized in the 1990s, you can compute the spectroscopy, you can compute the entropies, you can compute the heat capacities all a priori. So this is a pretty big advance too. Before that, you spent a lot of time doing calorimetry experiments. It was like very, very tedious to get good thermochemistry, but now all of a sudden, a lot of it you can just get pretty quickly. Because of this, quantum chemistry suddenly becomes super popular. It used to be an obscure side field of eccentric people who worked on super hard equations that they couldn't solve. And suddenly it became like every chemist in the world wants to have a software package that does it. And so I think in the 1980s, it was something like less than 1% of all chemistry papers had any mention of quantum chemistry stuff. And by the end of the 1990s, it's like 60% of the papers actually include a quantum chemistry calculation in them. The Nobel Prize was granted to Pople and Kohn for their work towards developing the quantum chemistry. And then Klippenstein and some other people developed methods for computing the rates of barriers of reactions. And if you want to hear about that, you should take the advanced class with Dr. Klippenstein. So this theory for transition state theory is for reactions over barriers. And he developed a method of how to do it if there's no barriers. So by the end of the 20th century, we could predict the individual rate coefficients a priori pretty well. And the accuracy was limited primarily by errors in the computed energetics. And most importantly, the barrier heights. So although we could compute the vibrational frequencies, the A factors, the entropies, the heat capacities, our H's weren't that great, and our barrier heights were really terrible. And that was almost always the error. But that was already pretty good, because then you could do a combined theoretical experimental thing where you took all the parameters theoretical for everything except for the EAs. And then if you had then you only needed a limited number of experiments to try to determine the EAs. So that turned out to be a semi-good method, and that was how people worked in the first decade of the century. But then by about 2010, these methods, the CCSDT F12 methods, became available and widely distributed. And they're so accurate that actually you don't even have to bother to do the experiment. You can figure out the EA directly. And so now I'd say that most of the barrier heights that are good that we have actually came from quantum chemistry and not from experiment. Whereas before, up to about 2010, it was almost all from experiments. So by the beginning of this decade, it's possible to do the calculations. And people knew how to do it, basically. And this just shows you sort of the advance. So back in 1997, 98, something like that, the B3 lit methods became available. And if you could calculate the thermochemistry of stuff. And so if we take the set of molecules that was originally TCT set, so there's a number of molecules where the enthalpies are known perfectly with very tight error bars, and you calculate how many molecules there are with how much error. This is like a histogram of the errors. It's very broad. You have sometimes you way over calculate, sometimes way under calculate. Each tick on these graphs is 2 kcals per mole. So here's like 0, and you'd have a whole bunch of 2, 4, 6, 8, 10. You have errors like 10 kcals in one direction, maybe 8 kcals in the other direction. And so DFT is just giving you like a ballpark number. So if you want to draw a cartoon of the potential energy surface, it was OK. But if you actually wanted to compute anything, it wasn't that good, because if you're off by 10 kcals, e to the 10 kcals divided by RT is like 1 kcal, so that's e to the 10th power. So you're off by a factor of e to the 10th. It could be plus 10th or minus 10th. And so you could be quite a broad, many, many orders of magnitude error just due to the energetics being wrong. A guy named Carl Melius from Livermore thought of a clever idea to try to patch this. He said, well, we actually know a lot of enthalpies from bomb calorimetry and stuff. So let's rig up some combination. We do some quantum calculation, and then we put some empirical corrections to that to try to make it better. And you can do it, and you can make the errors a lot smaller. So if you do that with BA3 lip, you get errors that are like 5 or 6 kcals per mole instead of 10 kcals per mole or 12 kcals per mole. So you get a much better error, but it's still, if you make a model like this, I've done it, it's disappointing. You get a model, it's kind of qualitatively correct in the sense you get the main reaction paths, but all the numbers are off with random errors of factors of 100 all over the place. So you definitely don't want to look at that on a linear plot. You can look at like a log-log plot. Sometimes you can see something. But really, it's not that satisfying if you're trying to understand something. If you have any possible question about two competitive pathways, you really have no idea, because one can be mispredicted 100 times too fast, the other 100 times too slow. And so you can have mispredictions of factors like 10,000 between the two. So you can be completely wrong if you predicted, I think this is the main path. So that's no good. I don't know when the time was, actually. Around 2000, I think, that this method, CBS-QB3, was invented. And this one is much more expensive than density functional theory, but right away gives really pretty good accuracy. So it has errors that are like after you make the empirical correction in DFT, you get that kind of accuracy directly from the method without no corrections. And for reasons I don't know why, this method corrects beautifully. And if you put in bond activity corrections, it's like the errors become really small. So all the errors are 2 kcals per mole or less for the enthalpies. So if you want to get enthalpies now, when you have the CBS-QB3 method, you can do great. And so for most of my career, this is the method that my students have always been using, CBS-QB3, to get the enthalpies. Well, we'll talk about this in a minute. Then more recently, they invented these F12 methods. And you can see the error for these methods without any corrections are sort of like this method with the corrections. And now if you put corrections on top of these guys, you get these really sharp things where you don't have any errors bigger than like 2 kcals. Mostly everything's less than 1 kcal. And now this is like basically as good as you can do the experiment. So now you can really get great numbers. However, this kind of level of theory, this is a significantly expensive computation to do. So you can only, today, you'd only be able to do it with molecules of maybe 6 or 7 carbon atoms. And that might still burn your whole computer budget for the year. Now, let's talk a little bit about these corrections. So you can see, like for CBS-QB3, it's just a brilliant improvement in the accuracy of the enthalpies. And so you'd always want to use it for the enthalpies to get your equilibrium constants really great. So you have a quantum calculation, say for this reaction, allo radical going to allene plus H. And this is what the quantum calculation says. It says this is what the potential energy surface looks like along the minimum energy path between the two. But I know this number is going to be wrong. And so I'll use my bond additivity corrections that are recommended for the empirical corrections. And so I'll actually say, I calculated it as 45 kcals per mole, but really it should be 41. So I make a 4 kcal per mole correction there. And then if I compare this to experiment, this is going to be pretty close. And then I go over here, and it says allene plus H. I calculated to have a thermochemistry of 103 kcals per mole using like atomization energies. But if I put in the empirical corrections, it goes down to 97. And again, that's way much closer to the experiment. But now I have a problem that I made two different corrections, one correction on this side, one correction on this side. They're different amplitudes. So now if I kind of extend in, these guys no longer match. There's like a mismatch because I had a continuous curve and I pulled one part of it down by a certain amount and the other part of it down by another amount. And then what do I do in the middle? And unfortunately, right in the middle is what I care about for the barrier height, because this is the number I want to know to get the rate. So for the thermo, I'm in great shape because this number is good, this number is good. But my rate now, I don't know. I have three possible numbers I could use. And which one should I really use for the barrier height? And so what typically people do is they like pick one direction that they like. So I pick this direction, and I'll use this red curve to make my calculation of the rate. But if somebody else wrote the reaction the other way around, they might go and use the blue curve. And then the two, your calculation and his calculation, would disagree. Even though you both said, I used CBS QB3 with this bond additivity corrections, what's wrong? My kinetic model is not matching up with yours. And this is what it is that if the order of which way they wrote the direction they wrote for the reaction actually would change the result they got. So this is not good. Right? You'd really prefer not to have this problem. It's not a huge error. But this method is used also in catalysis. You guys know about heterogeneous catalysis? So in heterogeneous catalysis, almost everybody uses DFT because the higher level methods are too expensive and have a lot of technical problems. And so DFT has bigger errors. So that means the bond additivity corrections are larger because they're trying to compensate for bigger mistakes. So you had instead of having a small change like this, it might be 10, 12, 15 kcals per mole shifts over these sides. And then the mismatch here could be quite large then. And then the models can be completely different depending which direction you wrote the reaction. And I think a lot of people in the field who do this are not aware that it actually matters which way they wrote it. And so you get the kind of random mishmash of results depending on how they did it. Today, if you do a really good job with the rate calculations, I talked about some of it. Dr. Klippenstein talked about more. There's even more details about it. But if you do everything the best way we know how to do it today, you get really good results. So this is, for example, a calculation that my students did, this dotted line. And this is the experiment that they measured the rate for this particular reaction. This is kind of a weird biradical thing. When you react them, it's pretty close. And here's another one. And so you have errors and maybe a factor of 3. It's kind of how the deviation between what you would calculate and what the experimental observable is. Now, some of you say, factor of 3, that's terrible. Right? But then you think, if we hadn't done the experiment, we'd have no idea what this number is. It could be anywhere, factor of 1,000,000. And all of a sudden, now we're down to a factor of 3 error bars. So that's quite a substantial reduction in the error bar without doing any experiment. So we just ran the calculation, boom, it ran. At the end of the week, we know the answer. So this is really a tremendous advance. All right, so we know how to do the individual species thermo. We know how to do the individual species reactions. We know that we can't write down that propane burns this way because we know it's a lot of elementary steps. It's really more like this. And this is actually only a piece of it, of the reactions. And this is all the list of reactions and A factors and N's and EAs, like you would have in a ChemKin file. And so the question is, how do we do that? So, experimentally, you mix up propane and oxygen, and you're going to make CO2 and water, but all these intermediate species over here, what the heck is C4H742, right? You might have no idea. And so how the heck would you do this? And, unfortunately for you, there's a high probability that your boss is going to say, oh, you went to Dr. Green's class, you know about building mechanisms now. Well, we have this new problem, and we don't have a mechanism for it. It's your job to do it, I'll see you in 6 months. Please come up with a mechanism. And some of my students are like, yeah, you've already done this to us. So let's talk about how you would do it. So this is a quiz question for you. How would you build a reaction mechanism? So suppose you have your favorite system, and suppose your boss, your thesis advisor, somebody who's giving you a lot of money to support you, says, OK, all I want you to do is build a better mechanism for this system. So what are you actually going to do? You have the normal situation. You know from your prior knowledge, from the literature, that there's some set of species that probably are involved in this reaction. And you might know a few of the numbers. They might be in the literature databases. And some idea of some of the reactions. And you also know from this course and your Dr. Klippenstein's course and stuff that there's actually a lot of different ways to try to calculate the rate coefficients and try to calculate the thermochemistry. And you might be able to find some of those numbers in data tables. And there's group additivity methods and all kinds of methods. So what are you going to do? You have the possibility to compute all these numbers. And you have some set of reactions. And now it's your job. What are you going to do? So that's the question for you. How are you going to proceed? I want you to try to talk to people around you and try to write down a few of the steps that you'll have to do on the way to getting from where you are today to this better mechanism that you're going to bring back to your boss and say, please give me a pat in the head and give me a promotion or something. All right, or sign my thesis or whatever. All right. All right, so let's have some things. So just, maybe somebody just raise your hand. Just tell me one thing of the many. There's going to be many things we have to do. So just one thing. Yeah.
Grab all the species that you find in literature and all the reactions that you find in literature with whatever rates you can get and dump it into one model.
Okay, so scour the literature. Combine into one model. So it's sort of like taking a union of the known models. All right, you're like sort of just combining. Yeah, okay. All right, any other ideas? What else do you have to do? No, somebody else. Yeah.
Run a sensitivity analysis on your new model.
Sensitivity analysis? Yeah, and this will be super important, right, to figure out which of the parameters we have to get better. Yeah.
You taught your reactants and products. So if you can identify all the intermediates, and then you can fill in the gaps, you can make predictions on transition states.
Okay.
There's different ways.
Okay, so try to fill in gaps to connect the known reactants to known products. Right? Because if you take the union of all the literature models, it's possible they might not even connect. If you type in propane and oxygen, they may not actually get all the way to CO2, right? It's possible. And certainly if you know that NOx is one of your products, it's a good probability that you're not going to connect to make NOx out of propane. Okay. And then there was a second thing about that was you're saying that do transition state theory calculations on some reactions. We'll have to figure out exactly which ones to do. Maybe sensitivity analysis might be one to tell us which of these we want to do. Other ideas? Yeah.
We can run it in a loop, like a feedback system, to check in on like a simple test cases, like a counterflow flame or something like that, to just check if they're like getting good results.
And are you going to be checking against experiment or against what?
Experiment, yeah.
Okay, so test your model versus experiment. This has a lot of there's a lot of different ways you can do this.
For simple cases, there are analytical solutions as well. So maybe
Analytical solutions for the model?
for a counterflow flame or something like that.
You can solve the model.
Yes.
Yeah, you can definitely solve the model. And actually, yeah, that's a good point. So you might want to model a system that you can't even solve. You're in big trouble. It might be true, though. For a minute, let's assume that you have a solver, that if you actually had a mechanism, you could solve it. If you can't, Professor Liu's going to tell you later this morning about what you try to do that next, if you get stuck in that bad situation. But we would assume that at this point, we have some way to solve the chemistry model to make a number that we could actually compare with the experiment, because otherwise we're in big trouble from the beginning, right? All right, yeah? Any idea? Any other ideas? Yeah.
We have all the reactants and all the products, so maybe have to find some way to find some other new reactions too.
Okay, so you need to find you need a method to identify additional reactions. So we have some amount of reactions that people in the literature told us about. We typed them in, but we think there's probably some more. So we have to have some procedure that we're going to use to figure out what new reactions we're going to add to our list of reactions, right? So this is a very important thing. Any other ideas? Yeah.
Some sort of a criteria on when you're going to stop developing the model.
Criteria for when we're done. When we're done. You could end up when you're done, if you're lucky, when you're done, the model is good. It could also be you're done because you tried everything you know what to do, and your model still stinks. Also a possible solution, possible endpoint, right? And so you do need a criterion when to stop. Just because you keep working on something doesn't mean it's going to get any better, right? If you finally misunderstand something, you could just work forever on the thing and it may never get any better. Yeah, any other thoughts? Yeah?
Maybe use machine learning to fit those criteria.
Machine learning, yeah, so what would you train your machine learning with, or what's your?
Maybe you can choose different rates in a reaction.
Okay, and then have experimental data you're training from? Okay, so if you have a lot of experimental data on your system, you can go back to the old-fashioned way, the postdictive way, right? And you can try to make models that are basically, you're going to use the experimental data to guide you in the model. Sometimes that's true, but I would say in combustion chemistry, almost never. Combustion chemistry, usually you're always data poor. You have very few data. So the machine learning has very limited ability to help you because you don't have a data set to train the machine learning from. So this is a bad, I mean, this is sad, right? I mean, we wish we had more data. So those of you experimentalists, get back to work. We need more data. Anything else we got to do? All right, so let's try to think of how we're going to do systematically. If we have a model that we got from the literature, and we did a union of no models, there's a first step issue here is that if you take the union of two models, it's highly likely that a lot of the reactions are going to overlap. Because part of the reason is that whoever wrote the second model second, they might have read the paper by the person who wrote the model first, so they might have just stole a whole lot of ideas from them. So you have an issue that you don't want to duplicate reactions. If somebody already has a reaction in both models, you want to just keep one. But often they'll have different parameters. They'll write down different A's and EA's. So you have to do some selection criteria about which of them you believe better, or you take the average, or whatever. You have to figure out something about how to handle that. But let's assume you dealt with that. And so you can make a union of no models. Then the obvious thing to do is if you think this model might be good, is you would do sensitivity analysis on it, find out what the key parameters are. And then if the key parameters are ones that you look up how they got the numbers, you read the papers, and some of the ways they got the numbers seems fishy to you, then you say, OK, I'll try to calculate this, or I might even try to measure it myself and get a better number. So that's like an obvious procedure. So there's sort of like the inner loop here is, we have a model. I'll call it model X. We analyze this model. Model X. And we refine the sensitive parameters. So whatever model we're up to, this is going to be an iterative process, right? You're going to get a model from literature. You're going to change it. Now it's a new model. You're going to rerun it, right? And then you might make bigger changes to it. And presumably this is going to be like an iterative refinement. As you work on it more and more, it's going to keep on getting better. It's like making a sculpture. First you kind of rough it out, and then you start to carve a little better. At the very end, you're using fine emery paper to really carefully polish, David's bottom so it looks really nice and smooth or whatever. So, you need to expect that that's what the procedure. But each time when you get up to the point where you say I have a model, you're always going to do this, right? Refine the sensitive parameters. And this might involve doing quantum chemistry calculations or something. However, you're going to get better numbers. And so that's the main loop. The issue with this never changes the structure of the model. This always has the same number of species. It always has the same reactions, right? Because you have a model, it has a list of some species and some reactions, and you can refine the parameters in those species and reactions as much as you want. In the end, you could run the highest level quantum calculation in the world on every single parameter in that model, and it still might not match the experiment because you might have left out some species or some reactions, right? So at some point, you're going to have to step outside this world of this model structure and add, where does it say? Method to identify additional reactions. You have to have some way that you can add additional reactions and maybe even add additional species. So you have to figure out, at some point, you run this for a while, you do refine the sensitive parameters. Maybe if you have some data, you could even test the model versus data. And actually do this multiple times. Refine, resensitive. Every time you change the parameters, you have to do the sensitivity analysis again. Run it again, run it again, run it again. Eventually, you get tired of doing this, or you think you refined all the parameters you can, as best you can. And then you're going to test to see if this model is any good. So you test model X versus data. And almost invariably, it's going to say, no, it stinks, right? So now you have to figure out what to do next. So the only thing you can do now is you already have all good parameters. Is you have to figure out how to add additional reactions. Right? So you need some procedure now to do that. And that will make this into like model Y, a different structure, because it's kind of additional. It's going to be a different size model, different reactions, all stuff. And then you can go do the same whole procedure again. So then you'll do this. And now you go back up to the top. Now you have a different model, and you do the whole thing, and you refine it again. And then after a while, you decide, OK, is it any good? And you test it. And if you're lucky, at this point, it says, yes, your model is great. It predicts every number within the error bars. And you're feeling great. Now you publish, and you get your thesis advisor to sign your thesis. And you're out of there, OK? But more likely, it still doesn't match. So then you go back, and you have to add more reactions and more species, right? And you keep on doing this. So we have to think of a way to keep how we're going to systematically keep adding more and more and more. Now, which ones should you add? There's a lot of reactions in the world. I told you there's 10,000 have already been measured. And then there's like, you know, you can imagine millions of possible reactions. And you're not going to dump all 1 million reactions into your model at once. Otherwise, your poor computer is going to complain. Right? Also, where the heck do you get the parameters for 1 million reactions? It'll take you a long time to calculate them all. So you have to figure out, like, you want to add like 1 reaction at a time or a few reactions at a time and kind of gradually build it up. And so you need to have some criteria, some procedure to recommend which ones to add next. Okay? So that's the whole sort of story. And then when you finally get one that you like, you finally say, yes, it's great. Then you're going to say, OK, now I want to run it in my engine simulation. And then you put it in, and immediately the code crashes because you're using too much memory because you have too many stupid species. So then you have to do model reduction. Right? After you have a model that, at least the big model, you believe it's true, it's really good, it matches some experiments, you're happy with it. Now you have to figure out how you can reduce it to make the whole solution time feasible at the end. All right? So this is our overall view of what we're going to try to do. So now I'll talk about how my group has done it, and it's not that different from what other people have done too. All right. So the question is, so for a long time the science question was, can I even predict the thermochemistry of a single species? Can I predict the rate coefficient of a single reaction? And that's not even a very complicated thing, as I told you about, and Dr. Klippenstein's class is all about that too. And you could actually take several more classes all about that topic. But after you've done that, you have an issue about, we actually want to predict the time evolution of a whole reacting system with maybe 1,000 important molecules, maybe 10,000 important reactions. And so we have to be able to figure out how to select, out of all the possible reactions in the universe of species in the world, which 1,000 and which 10,000 are the ones that really matter for our case. And right away, just things to keep in mind, if you're going to work with models that have 1,000 species and 10,000 reactions, you have to accept that most humans don't have the attention span to work effectively with a model that has 10,000 reactions. So this is going to be a problem. And then how the heck you're going to check if your simulation is correct if it's so large is a big problem. So you're going to have to figure out how to use the computer to help you to handle just the size of the model. Also, if you're going to do quantum chemistry calculations for the 10,000 reactions, that's a very large number to do. You have to figure out, how can I find 10,000 saddle points? How can I pay for all those very expensive electronic structure calculations and all the geometries I'm going to have to examine? So you're going to need a supercomputer. And I would say that in addition to high accuracy methods, you need low accuracy methods that work, because in the process of trying to select which reactions to include in the model, I need some kind of rule of thumb to have an estimate of how big is this reaction going to be. There's no sense for me adding in reactions that then I spend a lot of computer time to compute, and I find out that the rates are 10 to the minus 47th, and so it's of no value, right? So you want to figure out how you can identify quickly which reactions might be worth including, which really means you need some kind of good estimation procedure or some cheap calculation you can do to estimate if a reaction is really worthwhile to consider. And then just keep in mind, experiments only test some predictions of a model, and usually, very often, are not sufficient to determine any of the parameters, because each of the parameters, the connection between the data and the parameters is a nonlinear connection. And if you're trying to invert the process to go from the data back to the parameters, you can only do that in very specialized cases if you have a limited number of data. If you have fewer, typically fewer data than parameters, it's like an indeterminate problem. So very often, if you see a difference between your model and the experiment, you will get no information about what to change in your model to make it better. So that's a very unfortunate thing. So you'll know the model's wrong, but you don't know why it's wrong. And then you got to keep in mind that all the numbers in models always have uncertainties. And actually, all the numbers in the data, also in the experiments, also have uncertainties. And you really have to keep track of error bars and do uncertainty quantification, propagation of error bars correctly to say anything meaningful about it. All right. So as Dirac said, the chemistry is way too complicated. It's not, just to solve the equations is very complicated, and then the number of possible reactions and species is very complicated. So we need a black box to do it for us. And so ideally what we want, if we're going to go to like Ford or General Motors and say, here we're really contributing to the progress of solving society's problems, we want to actually give them a software that fits on their workstations that the engineers have at Ford and say, okay, you just draw a CAD drawing of your engine design. You say how much power it's being operated at. And we have a documentation of all the chemistry knowledge that's relevant to your fuel somewhere. We provide that. And they say what fuel they're using. And they click something about their operating conditions. And they want to send, the engineer would want to send this into their computer. And then they want to go get a cup of coffee and talk to their friend down the hall. And when they come back to their office, on the screen is going to tell them how much emissions are they going to get with that design, with this fuel, what's the engine performance going to be, and error bars in those numbers. And then they can then we're really making design, right? If you can get to that point, then this is really a tool the engineers would use. If you say, okay, you have to go get a supercomputing account and the calculation is going to take a month, then most of the engineers will immediately not be interested. Okay. If you say you have to go look up all the chemistry knowledge by going and reading all these chemistry papers in order to figure out what's important for your fuel, then I can guarantee you the mechanical engineers who make cars are not going to be interested at all. Okay. So this is a requirement. This is the ultimate goal. This is really hard. So instead, I'm going to work on a simpler thing. It's just, can we do 0D and 1D reactors where the flow field is simple and I can actually solve all the simulations. And we'll just do that to begin with. Eventually, we have to get to this. There's the real case. This is the real world case that we have to solve, is with the real engines. It's a pretty hard problem. All right. So we have some challenges. We have to be able to identify all the important reactions and species. We really don't want to include a lot of unimportant reactions and species because it would make us do more work with no benefit to our predictive ability. So we have to be able to somehow distinguish between what's important and what's unimportant in the species and the reactions. And then we have to do all the computations to sufficient accuracy. And some parameters we need to know very precisely because we're very sensitive to them. A lot of parameters, we're not that sensitive to them, and we could use really rough estimates. And so we could cleverly know when they're important and when they're not important. Then we could use very rough ideas like functional group extrapolations for a lot of parameters, and then spend a lot of our effort, focus our effort on the ones that really matter, that really affect the observables we care about, and do really fancy quantum chemistry for those, say. And then we're going to have all kinds of numerical and computer problems. We just have to anticipate. If you're starting from the premise, I'm going to end up with a model with 10,000 reactions, you've just got to expect that there's going to be a lot of trouble. And really, you want to try to get humans out of the loop. You want to minimize how much effort the humans need to be, because everything's going to be hard for a human. If they get an error message saying that reaction 972 had some problem, and then they go look at it, and then they can't figure out right away what it is, and then maybe it's because 972 is interacting with reaction 555. It's just like, that's like a whole day of some human's life trying to track it down. So you don't want to do it. You want to get as much of the stuff to be automated as you can. Now, a lot of people have worked on this problem for a really long time, and there's a really nice volume of Comprehensive Chemical Kinetics, 1997. It's all about this problem of how to predict things. And also Advances in Chemical Engineering, 2007, all about how to build the models, how to do this. So what I'm going to show you today, I'm presenting it, and it's mostly work that my group has done, but actually we're all part of a much bigger effort by the worldwide chemistry community to try to do this. All right, so at the time I started, and it might be the state that you guys are at now, many of you, is that you have a license to a code like Chemkin or Kentera, and you know how to run it. And if you somehow could get a list of all the reactions and array parameters, you can go and run it. Or you might have GT Power, you might have Kiva, I don't know what you guys have. Any of these programs, if you can give them all the reactions and all the parameters, and you press go, it'll convert them into differential equations, and then it'll actually solve the differential equations and give you predictions. And this has all been done since about the 1980s when people wrote Chemkin. And so this is, I assume that all of you have available to you software like this. And then so then the whole challenge is, where the heck do you get this long list of all the important reactions with all the important rate parameters? So the key ingredients, if we're going to use the computer, actually, no matter what we're doing, we need to know what the species are. We talked about that philosophically, to know what they are, and then we have to tell the computer what they are. Because the computer is going to keep track of species. It has to have some identifier for species. We then have to represent reactions between the species and keep track of them. Then we need the numbers. So each of those reactions has associated a bunch of thermo numbers and a bunch of rate numbers. We need all those numbers. So we have to have estimators and calculators to calculate all those numbers. And then we need this metric for how to decide which species and which reactions need to be included in the model. All right, so let's talk about that last question. So this is the situation we have. We have our model as assembled so far. It has some species, it has some reactions. Maybe we stole it from the literature, maybe we were brilliant and we thought it wrote down ourselves. Somehow we got a list of some reactions and some species. And we have that right now, and let's assume that we can get parameters for all those. So we actually have the actual rate expression. So we have a model we could integrate in Chemkin and solve it and predict the time dependence of these guys. But this model has like an artificial boundary. Is basically, it doesn't include some other species. So in the real world, everything can react to make everything. But in our model universe only knows about the 27 reactions we have in our species, in our model, and the 18 species, and that's it. And in the world of the model, all reactions that change these species into other things outside the model don't exist. They all have rate coefficient 0. They're gone. But in reality, they don't have rate coefficient 0. Really, if you have propyl radicals, you could actually make propene. It's definitely a possibility. You could kick out an H atom and make propene. Or if you have formaldehyde, an H can get extracted and make HCO. It's definitely a possible thing that could happen. And it has some real physical rate coefficient, even though our model doesn't know about it. Because if our model doesn't include HCO or include propene, it's not going to have any rate parameters going to those species because they're not even in the model. So the key is, can we identify reactions that we think should exist that were omitted from our model so far? So we'd like to go through and look at the species we have in our model so far and write a list of all the ways that those guys could react that has not yet been included in our model. And I'm going to call the species that you could make from just reactions of these guys among themselves. We'll call them the first generation byproducts. And later I'm going to call them the edge species. So we have the model, and then we have the species that are on the edge of the model. Like if we added one more reaction, we could get to these species. Okay? Now, there's a whole bunch of other species in the universe, and those guys take more than one step. To get from here to these guys, we have to go through these initial products, and then they might go react further and get to some of the guys. So we're not going to worry about all these other guys right now. We're just going to worry about the model and the guys we can get to in a single step from the model. And that's the key way to break up the world of all the chemistry. Stuff we've already decided to include in our model, stuff that we might add by just adding one reaction, and then everything else that might be hard to, we eventually might make, possibly. So then you have alternatives of how you could proceed. So the traditional one is called human selection. So you have somebody like Henry Curon who's really good, Manny Sarathi, Charlie Westbrook, and they go through and they look at the reactions. They say, I bet there's this other reaction here. Let's just put it in. Okay, so that's human selection. And they'll just add a reaction that makes one more species, and then they'll go to the thermo file, add one more species, the transport file, add one more species. And then they'll think, I put one more species in. It might be able to do some stuff, so they add a few reactions to that guy. So that's the one way to do it. And really, they're making judgments about what's likely to be important just based on experience or guess. Okay? Another idea is to go back to this picture and say, I don't want to make any decisions. I don't know. I don't know much about chemistry anyway. Let's just tell the computer to include all of these species. So we'll take these guys, and we'll just add all the species that you can reach in one model, in one step. So we just write a systematic method for the computer to go down and figure every possible way that these two guys can combine and write down every possible reaction. It's just like a combinatorics problem. And you can do that. And so some other people have done that. So there's like a package by Broadbelt that does that. And that's called generational growth. So we have our parent species, and then we have the first generation children species. And then if you have a lot of computer time, you can say, well, let's look for the second generation children. And you could go from all the first generation children and see all the children species that they can make, and on until your computer memory is full because you've added so many species that you've overwhelmed the memory because you have so many. Because at each generation, you can add a lot of possible species. Then another idea is directed growth. And this one is, let's say that we always think that big radicals always unimolecularly decompose into small molecules radicals. So that's what we said like happens in diffusion flames on the fuel pyrolysis side. That basically every time you make a big radical right away, very fast, it breaks up into little tiny radicals. So let's just assume that not only does that fast, but it's the only thing it does. We don't consider the fact that maybe some oxygen diffused over there and it reacted, or maybe two of these radicals get together and recombine, or anything else. We say, forget it. All the big radicals in our model are only allowed to break up into small radicals. Okay, if you do that, then you have like a directed growth. And that'll make you a much smaller model because it's like very constraining of what possible products you can make. It's saying it only allows for like beta scissions. Boom, 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 always get beta scissions. And then all I'll end up with is the small radicals. And that's actually the Stanford approach right now. The high chem approach is basically saying that. It's saying like, just forget about all the other stuff they can do. Mostly they go this way. Let's assume it's 100% that way. So that makes the model a lot simpler. And then finally, I'm going to talk about the way that my software works is called the rate-based algorithm. And this is kind of like directed growth or human selection, where you're trying to put in reactions that are important, but the difference being is you're actually doing a numerical test. So you numerically test, is this reaction really faster than all the other reactions at this condition? Is it a lot faster? If it's only a little bit faster, then we better include them both. Okay? And so you're going to do the effort to do this numerical test of the importance, and instead of pre-cooking the rule about what your model construction is going to do. And so potentially this has a possibility to catch mistakes that a human might have made or the directed growth algorithms might make, but maybe be smaller than this generational growth. The generational growth will get every possible product at each generation. This one will only select the ones where the reactions are numerically significant. And so you'll make a more tailored model. And that'll help keep the model size under control. I think maybe now let's stop now and we'll take a break for coffee.